Okay, welcome, folks. Uh, Special edition of school chemistry here. So we'll start chapter 10, which is our electrolyte solutions. Like how it's an expansion of our real solutions chapter that we just did, chapter 9. Chapter 10 is then building on that with all the solutions we were considering were just solutions that were non-ionic, non-ionizing. So this is just building on it to make electrolytic solutions. So first, before we get too far into this, we need to consider the enthalpy, entropy, and Gibbs free energy of ion formation. What does it take to form an ion in solution? So focus on the electrolytes. So the compounds that essentially dissociate into positive and negatively charged mobile solvated ions. We consider them dissolved and sufficiently polar solvent. So just considering the reaction of hydrogen gas and chlorine gas breaks down into hydrochloric ion gases. And consider the same thing, hydrogen gas, essentially breaks hydrogen proton gas and a chloride gaseous ion versus that same thing with an aqueous solution. So two reactions. The only difference is the phase of these two products. Now, the first reaction has an enthalpy of 1302 kilojoules. So very endothermic, takes a lot of energy to split that apart. The second guy, the aqueous one, where we bubble these into solution, suddenly it's exothermic by 167 kilojoules. Not a whole lot, but still enough that this huge reversal results in something that's now most likely spontaneous. This difference is that it shows the hidden meaning of what it means to be aqueous, in that a solvation shell of water that will generate more energy than is gained than merely separation of ions. So just to take the two ions and break them apart is one thing, but to break them apart and then encapsulate them in water is entirely another thing. Entirely really big thing that's going to change the energy entirely. Now, back in chapter 4, we talked about how we calculated delta H reaction. We set our pure elements in their standard state enthalpy to 0. So that meant that the delta H reaction for this is just the sum, for that reaction is the sum of the delta H of proton, the delta H of chloride. But the problem is we can't, once again, we cannot measure an individual ion by itself. We can't measure one without the other, because you always have a cation and an anion. So same way as we couldn't measure an absolute enthalpy because there was no 0 point and you have to measure something based on something else. Can't measure an ion without another ion. But we do know that when we form an ionic solution, it's going to remain neutrally charged because there's equal amounts of positive and negative generated. So once again, we're going to do an artificial 0. We're going to say that hydrogen, the hydronium ion, is our artificial 0. We're going to say H plus is our 0, and we're going to use that as our ruler to measure everything off of. So the enthalpy of this reaction, the H plus and Cl minus, we're going to just measure Cl minus and say H plus is 0. And then if we measure something, say, instead of H plus, say Li plus and Cl minus. And if we know Cl minus, we can measure Li, so on, and daisy chain this way down the row. So we set delta G for H plus to be 0 for all temperatures. So delta S formation for H plus will be the how does delta G change with respect to T at a constant pressure? And so that actually becomes 0. Because delta G, if we said that, it's 0 for all temperatures. So we have our delta H, we have our delta G, our delta S, and our delta H for hydronium formation being 0. So with that in mind, we can measure our entropy chlorine, we can measure our Gibbs of chlorine, chloride, and our enthalpy of chloride without any problem. And we're going to convert, and you can use this to measure another cation and then another anion and so on and so forth until we have every cation and every anion. Now, because of this, the nature of this, these guys are going to be the only guys that are going to potentially have a negative entropy because of the solvation shell. Almost every other compound will have a positive entropy. But because we're measuring this actually off of H plus as an artificial 0, if they are less entropically favored than H plus, then it's going to have a negative entropy. If they're greater, you can still have a positive entropy. So here's some broad statements about H, G, and S made. We can still say a negative H and negative G means the formation of the ion is more exothermic or more spontaneous than H plus. Generally speaking, smaller ions will have larger negative enthalpy due to greater electrostatic attractions. And also we will multiply the charges for charged ions. So like 2 plus will have greater electrostatic attractions than say 1 plus. The entropy of these guys will be the measure of the immobilization by the solvation shell. So small molecules and multiple charges will have greater immobilization, and thus we have a negative entropy. So essentially, how well can we encapsulate this ion? So say beryllium 2 plus probably has a negative entropy, while say cesium 1 plus being bigger and only charged 1 probably have a positive entropy. So how do we measure the energy of solvation? We can experimentally determine this like most steps in this process. The only one we can't experimentally determine is energy required for individual solvation. So we're looking at this. How much energy does it take to split this ion? How much energy does it take to split this ion? Or split this compound into a neutral radical? How much energy does it take to, what's the electron affinity? What's the ionization energy? We can calculate that. The only thing we can't calculate by itself is the delta G solvation. How much energy does it take to solvate both of these? We can't determine one without the other. So we can figure out this. We know the sum of all these steps, including these 2 steps, will add up to this. We can estimate this through a model using a non-expansion work for a reversible process. Measure the difference in work to ionize a compound to charge Q in both a vacuum and a uniform dielectric medium. So you essentially have a solution with a uniform conductance versus solution in a solution in a compound in a vacuum, and we're ionizing it and seeing how much energy difference there is. That's going to be our Gibbs solvation. So the difference in work between this in solution and this in a vacuum will be our delta G solvation. Now, a few quick definitions. Atomic charge Q is in coulombs. It is composed of the number of coulombic charges of an electron times the number of electrons added or missing, so our Z. So that Q is the number of electrons Z times an electron itself. So the charge of electron times number of electrons. So 2 plus would be 2 times electrons to give us a total charge. Now, electrical potential are what? Phi is in volts, and it depends on the charge divided by 4 pi and the permittivity of free space, which is the ability of a charge to move through a vacuum, and the distance the charge has a spherical radius of center R. So essentially 4 pi is a constant, this is a constant. The only difference, the only real thing is Q and R. So how big is the ion and how much charge does the ion have? So for example, looking at beryllium 2 plus versus calcium 2 plus, they would still have the same Q, but the ionic radius would be different. So R would change. So the electrical potential would be different for those two. And when we calculate electrical work, we're integrating like our potential times the change in charge to get a unit of where Q is in coulombs, and we have volts and potentials in volts. And so coulombic volts becomes a joule. So we're integrating that. How does this change when we integrate Q? Okay. So when we approximate this, so the work of creating that charge in vacuum is W. So what charge in vacuum, W equals, we're integrating from 0 to Q, where we have this whole thing is our stupid little electrical potential. From 0 to Q, so Q dQ goes to Q squared over 2. So that goes from 4 pi to 8 pi. Now, the work in a dielectric medium must also include the relative permittivity of the solvent. So you get the same thing, except now you have a new constant that is solvent dependent. Like epsilon R. So this difference, it will be the work, will be the delta G of salvation. So essentially 1 minus 1 over epsilon R. So we can solve for this to calculate the charge on a molar level. We get, so turning Q into Z, it's Z squared, E squared. We want to turn this into molar, so we multiply electrons by Avogadro's number to turn it into moles. Keep all that the same. So bringing that out, we're saying calculate delta G solvation. So solvation, we're minus the constant of the vacuum. So that's why we flipped around 1 minus epsilon R minus 1. So that's a constant, all that constant. The only thing that really changes is maybe R. So we'll get this and simplify it even further. So, but there's some problems here. The model does a very poor job comparing delta G solvation calculated conventional thermodynamic values when you use the ionic radii from a crystal structure. So if we look at the crystal structure predicted by a X-ray crystallography, you say we got a crystal structure, this is what we expect this size to be. You just see this deviation right here. You see right here, this line is where we expect it to be, and this is what you actually get. There's going from barium to magnesium. There's lanthanum, chromium, iron, aluminum. Those are shooting way off the scale. So there's a way to fix this, but you have to use the effective radius, which includes some effect of the solvation shell. You have to say how much water is binding to these ions and thus increasing the radius. There's still some uncertainties with this. So there's still errors of plus or minus 50 kilojoules within your delta G and delta H, and errors plus or minus 10 joules in your delta and your S of solvation, but these are acceptable. I mean, it's not really good for many calculations where you have to be correct, but you can get it still somewhat close. But as I said, if we use the effective radii, you see they're fitting pretty closely to that line. There's a couple that are below and above, but it's still a lot better than it was. A lot better than it was. So what to say, is it great? No. No, but it's getting there. So if we have to get in our activity and our activity coefficients again. Standard activity and activity coefficient from the last chapter will not be sufficient because our non-electrolytic interactions on a short range between the van der Waals forces, electrolytes will experience very long-range electrostatic interactions. In addition, we see the separation of solutes into both positive and negative ions. So previously, we could have said that the Gibbs, the molar Gibbs of a solution was equal to the moles of solvent times the chemical potential of solvent, plus the moles of solute and the chemical potential of solute. So splitting it into solute and solvent. But now we have to specify. So we still have this solvent, but now we have the moles of the cation times chemical potential of the cation, plus the moles of the anion times the chemical potential of the anion, which we can further abbreviate as the total moles of solute equals the coefficient of cation times the potential of cation plus the coefficient of anion, the chemical potential of anion. Basically, that nu, the V, is essentially saying if it's sodium chloride, there's one sodium, there's one chloride. But if it's sodium sulfide, you're going to have two cations for every one anion. If it's sodium phosphate, there's going to be 3 sodiums for every 1 phosphate. So you're taking into account the charge, say how many cations you form for every 1 anion dissolved. So from there, we're going to use something called the mean ionic chemical potential. This is the first time we can actually do some math for this chapter. So rather than look at the positive and negative values separately, we're going to look at them as the average chemical potential between the two because we can't have one without the other. The reason being that we can determine this mean experimentally. While once again, the individual values are inaccessible. We can't find one without the other. So what we're doing, the mean chemical potential is using that plus minus. That chemical potential of both plus and minus is equal to the sum of both of those divided by the overall coefficient. So if that is 2 and that is 1, the overall coefficient is 3. So 2 times chemical potential plus 1 times chemical potential divided by 3, you get the average. That's 1 and that's 1, you're going to be divided by 2. So this mean can be applied in all aspects where we use chemical potential. So our mu naught plus RT ln A, ln alpha, the activity, becomes mu plus minus equals mu plus minus naught plus RT ln A plus minus, or the mean activity. So our mean ionic activity then becomes, we're going to take the activity of the cations times the coefficient of the cations times the activity of the anions raised to the power of the coefficient of the anions, all divided by square rooted by the factor of the total number of all ions. So, and this is due to the nature of what is a log. We cannot just add these together and average them, because this is within a log. We raise them to the coefficient and multiply instead of adding. So remember, the rule of log says, I'm going to annotate this real quick. Rule of log says a log x equals the same as log x to the 8th power. That's where we're getting that. We're taking that mu, or essentially the activity, log of activity, raising that to the power of b plus on that first term. And we say that log x plus log y can equal log x times y. Another rule of log, so that essentially the ln a plus and plus ln a minus, we can bring them together. And that's what we're doing. So that's why it looks so weird right there, because it's within a natural log that we're doing all this to. Okay. Now this further can be applied to mean ionic molality and activity coefficient. So with activity being molality over molality star times molality naught times activity coefficient. So that now becomes, we can have molality, the average ionic molality being the same thing. V plus molality times V plus raised to the power of V plus, V minus molality raised to the power of V minus square root of factor of V. Can take all that out. Take all that out. So that's a constant. So that's a constant based on your ions, and activity coefficient kicks into that because the overall molality doesn't change. This may, so essentially activity coefficient is going to be this, that. It's like, okay, so we have essentially a way to abbreviate our activity in terms of molality and activity coefficient. It's a messy little, like hot mess. It can be done. So from there, okay, so now substituting that in for our chemical potential solute. So where chemical potential solute has gone to the mean ionic chemical potential, which can then be the standard mean ionic chemical potential plus RT ln activity raised to the power of V. The mean ionic activity raised to the power of our coefficient, which then can be exchanged for our mean ionic molality over standard molality raised to the power of coefficient nu times activity coefficient, the mean ionic activity coefficient raised to the power of nu, which then can be simplified into the mean ionic molality, can be split into there's the factor of our coefficient coefficients of each one. Now, because we'll be taking a v outside, that square root of v, they're going to end up being canceling out. So it's just essentially the effect of the coefficients of each guy plus the new RT ln molality over molality naught plus new RT ln activity plus or minus that mean ionic activity. Now, because the mean ionic chemical potential, standard chemical potential is constant, and the coefficients are going to be constant for a given compound, those two terms can be absorbed together to give us our mean ionic activity double naught, or the standard mean ionic activity for a given compound. And that then gives us the mu, or new RT ln molality over molality naught. So that's going to be more or less constant for a given solution, given concentration. And then the only thing that really is unknown is our new RT ln mean ionic activity coefficient. However, now that since this is going to be our chemical potential for a solute, and that essentially our molar Gibbs, we can now essentially calculate the activity coefficient experimentally. We can find out what's the activity coefficient for a given solution by doing experiments. So the question is, why do electrolytes deviate so much? Well, for electrolytes to approach an ideal solution, we need really dilute solutions. There is a greater deviation at much lower concentrations than at non-electrolytes. Because in non-electrolytes, we only have very short-term close van der Waals interactions. And so when you get them further and further dilute, there's less likely chance of, in their small little sphere of influence, interacting with another molecule. So you don't have to dilute it by nearly as much to keep a molecule B from another molecule B. Obviously, you can't keep a molecule B from a molecule A, it's surrounded by it. But if you can keep a B from a B, you can essentially keep all the interactions more or less the same. But in electrolyte, we have very long-range attractive force of these. Now, as I was saying, electrolytes have very long-range electrostatic attraction and repulsive interaction. So like the cations will be repelling the other cations from much further away. The cations will be attracting the other anions from much further away. So we have to get them even more separated, even further away. It's like saying the non-electrolytes would be like having maybe short-range missile capability. They can reach and shoot other countries maybe around them. But electrolytes, we suddenly got like intercontinental ballistic missiles. We can shoot this across the globe and hit someone so far away. So we need to get these guys farther and farther away. We put these electrolytes on essentially different planets. Well, they can't hurt each other anymore. But we get these guys electrolytes more and more dilute to get the same level of isolation, keep A plus away from A minus, and only see them B, or B plus and B minus to keep them away from the solvent A. So since the interactions will only depend upon the charge and separation, we can still model them without consideration for the molecular identity. So we won't have to worry about the cation, whether it's a lithium or sodium or whatever. We just care about the charges, because the charges will still see each other from far away. And so this is where we're going to get to some actual math, and how are we going to model this? And this becomes the Debye-Huckel theory. It's a method for calculating our activity coefficient, developed by Peter Debye and Erich Huckel. Now, the solute will give rise to a spatially dependent electrostatic potential phi if the spatial distribution of ions is known. So, however, this electrical energy is small compared to the overall thermal energy. So we say the absolute value of the positive negative phi times the number of electrons times the electrostatic charge is always much, much smaller than the Boltzmann's constant times the temperature, which is our thermal energy. Now, the dependence of phi on the spatial coordinates and the spatial distribution of the ions around an arbitrary central ion can be calculated. And so you're saying I'm going to take an imaginary ion in space and calculate the electrostatic potential around it. So just consider first an isolated ion in a solvent, just one ion. I know it's hypothetical. One ion of radius r. The electrostatic potential was our Q, which was ZE. So it doesn't matter whether plus or minus. So plus or minus ZE, 4 pi, the permittivity of free space, the permittivity of the solvent, and our radius. Now add an ion to this dilute solution. So now the ion, so we still keep the original thing, but now we're adding raised to the power of E kappa R. So this kappa is an inverse of the Debye screening length. So it's essentially, it's more or less a constant for a given thing. But essentially, kappa squared is equal 1,000 liters per meter cubed. And this is just a unit to get this into the proper units. Electrons squared, Avogadro's, the molality and the density of solution times all this is essentially constant. The total number of coefficients of the cation times the number of electrons, so the charge squared, plus the total number of coefficient of the anions times the charge squared over constant, the permittivity of free space in a vacuum, permittivity of the solvent, Boltzmann's constant, and the temperature. So for a given solution, the only true variable that you could look at is the temperature. Is the molality, the only true variable is molality at a constant temperature, and molality and temperature at you leave everything else changing. So all this is, so you'd have to take the square root of that to calculate for kappa. But so just looking at the units there, this is the 1,000 meters per, is to get this into units so that R can cancel out. So if we compare the electrostatic potential isolated ion to a dilute solution, we see that the potential falls off with the distance at a much faster rate as concentration increases. So looking at this, at a concentration of 0.001, as R is getting further and further away, you see that this is say the actual chemical potential versus the chemical potential of an ion. So R is getting bigger, saying, how does this change? We see a very, very small change over a period of time. Or concentration is 0, let's say there's no change. So it's like dropping off. So that means what the isolated ion is greater than essentially the electronic potential is dropping as we get further and further away when it's constant, when it's dilute, and then we increase by a factor of 10, and suddenly as we get further and further away, it's dropping off by a much greater factor, and we get even more concentrated. The chemical potential for our solution is dropping off very rapidly, such that when we get it, so this is when R is increasing. So basically, the chemical potential is like when we get too close, we see this great deviation. The chemical potential of the solution is dropped off almost entirely just by saying like 4 times 10 to the negative 9th meters. What's that? That's 4 nanometers away, and it's like there's almost no chemical potential. We've lost it all compared to the solution. Now, with a 0.01, we're saying we're almost lost all of our chemical potential, relative chemical potential, by 10 nanometers. With 0.001, we've lost almost 50% of it by 40%. We're down to like 60% loss by 10 nanometers. So saying like the more concentrated, the more we're going to screen the chemical potential, the more we're going to block other molecules from seeing the solution, the more we're going to say like, hey, pay attention to me. So we're going to see this drop off as concentration increases. Now, we can look at this as an arbitrary central ion. So why is this happening? Ions of the opposite charge will try to surround the central ion. So like if we're looking at this negative central ion, we're going to have these cations trying to surround this. It's analogous to electron cloud shielding the nucleus. So as we move away from that central ion, the potential will get effectively more heavily screened and fall off. So as we go further and further away from the central ion, the solvent won't be able to penetrate through these ions, and we'll see it lost. By at greater concentrations, we're going to have better screening. So we're not going to see these long-range interactions nearly as well when we have more ions surrounding it. Just like the more electrons you have, the better the screening shell you have on a nucleus. So we're going to combine all this together to have something we can calculate with ionic strength. Well, ionic strength, I, is our molality divided by 2, the sum of our coefficient of the cation times the charge of the cation squared, plus the coefficient of anion times charge of the anion squared. You can factor that in for the molality of each one, but this might be easier. But so this can essentially, why is it the sum? Say you have more than one anion, so you have to take all that into account. By including this into our kappa, we can separate the variables from the fundamental constants. So all this becomes I over epsilon of what? So you can separate all those, which is a constant, from I, epsilon of the solvent, and density of the solution. So solution dependent, solution dependent. And I is the only thing that we can really calculate. So we get this as a constant, 2.91 times 10 to the 10th times square root of I, density solvent, epsilon solvent. Now the final units of kappa are inverse meter, and the factor of 1,000 liters per meter cubed is how we're going to get to that inverse meter. That essentially enough things cancel out here, here, here. So the moles cancel out, the Boltzmann constant cancels out a lot of things, so that you're left with 1 over meter squared, which square root Gets us to meters. If you follow all the units very carefully, you should get to 1 over meters. But that's just going to be important when we have that e to the factor of negative kappa r. R is going to be in meters. But finally, before we actually do math, is the Debye-Huckel limiting law, saying that our Debye and Huckel were able to create an expression for calculating the mean ionic activity coefficient called the Debye-Huckel limiting law. I'm going to say the DHLL. And the natural log of the activity coefficient, the mean ionic activity coefficient, is equal to negative absolute value of Z plus and Z minus. So the charge of each sum of the product of the charges times our electrons squared times kappa over 8 pi epsilon naught or epsilon 0 epsilon r k sub b t. With for water at 298, this becomes, taking all the constants out, the natural log of this is negative 1.173 Z plus Z minus square root I. So you'd have to change this epsilon r for a different solvent, but essentially say that we can calculate the activity coefficient by looking at the sum of the chart or the product of the charges times ionic strength. So it's named because this only works at small values of ionic strength. So if the ionic strength gets too high, it's going to deviate too much and we can't figure it. But this essentially predicts a constant decrease in activity with increasing concentration. So we can say that, show that, oh, this is going to start to deviate too much, is not going to split apart as well as it should as the concentration goes up. But okay, so let's actually try to calculate something here. I know this has been a hot mess of brain-meltingly difficult math. So let's actually look at these guys in practice. So what would the ionic strength and mean activity coefficient be for a 0.0004 molal solution? So a 0.4 millimolal solution of calcium phosphate. So I purposely chose calcium phosphate so we would have some interesting V's and Z's. So our molal, 0.0004. So we have 0.00 divided by 2. The sum of these guys together. So this guy is our V plus, this guy's our V minus. We got to add all these guys together. So we have 3 times, what's the charge of calcium? Calcium's 2, so 2 squared. Technically positive 2, but when you square it, you get rid of that. So that is 4 times 3, which is 12. Now we have the coefficient of this is 2. The charge is negative 3. Negative 3 squared is 9. 9 times 2 is 18. Add those together. 18 plus 12 is 30. So our ionic strength is 30 divided by 2 times 0.0004. So our I, right, our ionic strength is 0.006. So there's our ionic strength. We're going to use that in our next thing. So what's our mean activity coefficient? So how does this deviate? Activity coefficient being 1 would be perfect. So for water, ln y plus minus equal negative 1.173, absolute value of what? 2 positive times 3 minus, going to be negative 6, but the absolute value of that to give it positive 6, square root of 0.006. So 6 times let's do the square root of 0.006 times negative 1.173. That'd give you negative, the ln of gamma is negative 0.545, what would you say, 16? Now we have to take the inverse log to find what is our activity coefficient, and at that seemingly dilute concentration of 0.4 millimolal, the activity coefficient of this guy is 0.5797. So activity of 0.5797 at this crazy dilute solution. Now, since this is, let's consider, let's clear this. Let's consider the same solution, but instead of that, hypothetically, what if it was just NaCl? How would that change things? Well, let's look at our I. Our I would still be molal, 0.0004 divided by 2. But now the coefficient 1 times 1 squared is 1, plus 1 times negative 1 squared, also 1. So our effective ionic strength would be 0.0004. So not, the molality would be the same as what we would expect for the ionic strength. We've summed up 1 squared times plus minus squared. So now when we calculate the we calculate our activity coefficient, it's going to be a little different as well. So still going to have the negative 1.173, but now our absolute value of 1 times 1 is times 1. Square root of 0.0004. Negative 1.173 times square root of 0.0004. This gives us negative 0.02346. And now we take the absolute value, the inverse log of that. So sodium chloride of the same solution would have been activity coefficient of 9768. So sodium chloride of that dilution would have almost no decrease in activity. But this guy, because it produces 5 ions total, each with a pretty strong electrostatic charge, sees a drastic decrease in our activity coefficient. So you can see here's where greater charge has a much greater effect. And so it depends on what you're dissolving with how big effect they're going to have. Now, this last slide before we stop is the deviation. So While this Debye-Huckel limiting law predicts a constant decrease in the activity coefficient, we actually see that activity coefficient slows down its decrease and eventually begins to increase above 1 when we get high enough ionic strengths. This deviation is based on the assumptions made in the model, that ions are treated as point charges with no volume, and the finite volume results in an increase in repulsive forces that eventually increase with concentration. In addition, the model does a pure job take into account the minute poor job, taking into account the minute effects of concentration on the relative permittivity, vis-a-vis like how does the solvation shell change. And then, of course, empirical models such as the Davies equation are used in attempts to better model this deviation. So there's ways to model it. We're probably not going to worry about it. With that in mind, that's where I'll stop for right now. Yes, I know there's this is not exactly what I'd call easy stuff. That's why we're getting into the real hardcore stuff right now. So if this was informative, please like, please subscribe, and I'll catch you in another video.